Okay, so we've got this asteroid, Bennu, and we've recently put a spacecraft called Osiris-Rex into orbit around Bennu. And Bennu is known to have a mass of 78 billion kilograms. So that's 7.8 times 10 to the 10 kilograms. It has a radius of 262 meters. And the orbital radius of the Osiris-Rex spacecraft is 1,750 meters from the center out to the spacecraft, and it's in a circular orbit. So we want to know, for this little tiny asteroid, this is a very small asteroid, how much would an astronaut weigh if they were standing on the surface? And just assume a 75 kilogram astronaut. Now, an astronaut would probably also have a big spacesuit on, which would at least double their weight, probably. But we'll just say, let's put, how much would they weigh standing on the asteroid compared to, like, the Earth or something. Then we want to know, what is the speed of the Osiris-Rex orbit? And what is the period of one orbit? So for part A, here we've got our astronaut. This is not to scale, but standing there, and they've got a mass of 75 kilograms. So we know that there's an attractive force between the mass of the asteroid and the mass of the astronaut. So, and the force of gravitational attraction between two massive objects, we know it to be the gravitational constant times the mass of the asteroid times the mass of the astronaut divided by the distance between them squared, and the distance from here to here, from the center of the asteroid to the astronaut, is just the radius of the asteroid. So now we can plug in our values. Big G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. A lot of you are skipping the units. Don't skip the units because they do help you make sure that you're doing things the right way. Now the mass is 7.8 times 10 to the 10 kilograms. Am I still on screen? Barely. And then the mass of the astronaut is 75 kilograms. And then we're going to divide this by the radius, 262, this should be squared, I'm sorry, meters squared. And by the way, I forgot to put the square on there, but because I use units, I would have caught that mistake, because I know I need to cancel out this meter squared with the squared meter on the bottom. So showing your units is always a good way to catch your mistakes. So let's get this calculator out, and I got 6.67 times 10 to the negative 11 times 7.8 times 10 to the 10 equals 5.2 exactly. Then we'll multiply that times 75, and I get 390. But then I'm going to divide that by 262 squared, and I get this very small number. It's in scientific notation, but I'm going to put it in 0.00, let's see, 1, 2, 3, 5, 6, 8 newtons. Now, that's really, really tiny. Yeah. That's tiny. That's less. You would have less weight. You would weigh about as much as like half an M&M. I think half an M&M probably is about that weight. You would have the weight of a drop of water. And so if you were standing there and only this force was holding you to the ground, You make the slightest little twitch with your calf muscle or whatever, and off into space you'll fly. You can't really walk on an asteroid this tiny. And now this is about the size of a hill. You know, I mean, it's a nice big hill. So it really is a very small object. Now, for part B, what is the speed of the Osiris-Rex orbit? Well, we have this equation that we derived, and I'll let you use it. So this is the orbital velocity equation for circular orbits. And so G is, again, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Now pay attention, please, because this M right here, the M in this equation right here, is the mass, thank you, of the thing that you're in orbit around. Now you have two masses given. You've got the mass of the astronaut, the mass of the asteroid, and the mass of the astronaut. Which one should I use? The asteroid. Now this, we're in orbit, right? So we want to use the orbital radius. Not the radius of the asteroid, but the radius of our orbit around the asteroid. And that's from the center of the asteroid out here, but it was given to be 1,750 meters. So let's do this. .67 times 10 to the negative 11 times 7.8 times 10 to the 10. Then I'm going to divide that by 1,750. And I get a tiny number, but I got to remember to square root it. And I get 0.0545 meters per second. This is very, 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 very slow. What is this right here? This is 0.05 meters. That's 5 centimeters. It's traveling 5 centimeters per second. Well, 5 centimeters, it's like this much. Actually, that's more, like this much every second. So it's literally moving this fast around the asteroid. So it's going to take a long time to go around once. Let's see what that orbital period would be. Well, we also know that orbital velocity is equal to 2 pi r over the period. And so we can solve for the period is 2 pi r over the orbital velocity, which we already got. So this is 2 times pi. There is another equation we got for period. And if you want to use that, you can. It's a pretty complicated equation, though. This is a little bit easier to do it this way. Now, the orbital radius is 1,750 meters. And the velocity is 0.0545 meters per second. So when I do the arithmetic, let's see, 2 times, 2 times pi times 1,750 divided by 0.0545. I get 2.02 times 10 to the 5 seconds. Well, let's see how long that is in hours. We know that there's 3,600 seconds. I mean, this is your answer right here, but most people don't have a feel for how long that is, so let's figure it out in hours.
We can't see.
Oh, thank you. So 2.02 times 10 to the 5 seconds, that's what I got. So I'm going to divide that by 3,600. And I get 56 hours. And just divide that by 24. So it takes about a little less than 2.5 days to go around the, well, it says 2.34. Am I still on? Yeah. Days. So, or you can use that. So, you know, a lot of the stuff that we did, you know, we did some stuff with black holes the other day. Now we're doing this. This is just like the opposite. I mean, this is so, this asteroid is just so tiny that even with an, you know, this orbital radius is about, well, it's about a mile, a little more than a mile from the center. So the radius is a mile. So you go around here, it's probably about 7 miles circumference. Okay, 7, maybe 8 miles. It'd take you 2.34 days to do that. So you're moving really, really, really slow. So this spacecraft, Osiris-Rex, has very low force thrusters, but very, very precise thrusters on it that allow it to maneuver around this object. Okay. Any questions? Okay. That is